Hi class, this is Getting Started with Probability. We've divided the module up into 16 lessons. The first few are just the basics: experiments, sample spaces, events, what's probability, etc. The next three are counting techniques. That has to do with efficient ways to count things. Lessons 8 through 12 deal with applications arising from these counting techniques, and lessons 13 through 16 concern conditional probability, the concept of independence, and what's known as Bayes' theorem. The next few lessons start from here, then go into the definition of probability, basic probability results, and finite sample spaces. So to begin, let's consider a random experiment whose outcome we can observe. For instance, you can toss a coin. You can see heads or tails. You can toss a coin 3 times. You can ask 10 people if they prefer Coke or Pepsi, and I really hope here in Atlanta that they prefer Coke. And we can also see how long does a light bulb last. Our first definition is that of a sample space. A sample space associated with an experiment is just the set of all possible outcomes of the experiment, and it's usually denoted by S or the Greek letter omega. Here's some examples. Let's go to that coin toss. When I flip the coin 1 time, I get heads or tails. That's it, nothing else. Those are the only possibilities. So the sample space is heads or tails. The outcomes from 3 coin tosses could be a little bit more complicated. Let's look at kind of the obvious thing. Here's a sample space of all the sequential tosses. Heads, 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 tails, blah, 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 all the way to tails, tails, tails. There's 8 of these things. And these are all the combinations in order of potential heads or tails. And that might be just fine. That's the one that I would do first of all. On the other hand, if your experiment was just to count the number of heads that you observe, then we could do a slightly different sample space. Let's call it S prime equals the number 0, 1, 2, 3, corresponding to the number of heads that you see when you toss the coin 3 times. So this illustrates that a sample space doesn't have to be unique, and what I'd say is try to pick your sample space so that it answers the question that you're interested in your experiment. Going back to the Coke or Pepsi example, the sample space here is just the number of people who prefer Coke, 0, 1, 2, all the way up to 10. Let's make sure they're integers. And a slightly more complicated sample space is the lifetime of the light bulb. And you can have any real number greater than or equal to 0. I guess you'd run into a 0 if you had a defective light bulb that didn't even work when you turned it on or it blew out immediately. Other than that, it's going to last some lifetime greater than 0. Let's do another definition. An event is just a set of possible outcomes coming from the sample space. So any subset of the sample space is, by definition, an event, any subset. For example, I know we have several D&D fans out there. So let's suppose that we take one of these 8-sided Dungeons & Dragons dice, and let's look at the sample space there. 1, 2, 3, up to 8. There's 8 sides, 8 numbers. And if you're a tiny little elf, you may be interested in the event A, that an odd number occurs when you toss your die. So in that case, A is just the subset of the sample space consisting of the numbers 1, 3, 5, and 7. So when you toss that die, you get a 1 or 3 or 5 or 7. Very, very easy. One remark is that the empty set is always an event of the sample space. This actually makes sense, the empty set or null set, because the empty set or null set is a subset of any set. And so therefore it's a subset of the sample space, and therefore by definition it's an event. It corresponds in plain English to none of the possible outcomes of the experiment are observed. And you may say, well, that's not very unlikely, and we'll see in the next lesson that the empty set almost always, actually always, has probability 0. And we'll see that coming up. Similarly, the sample space itself is an event because any set is a subset of itself. So therefore, the sample space, it's a subset of itself. It's an event. And that corresponds to the event that something from the sample space happens. And you might say, well, that's pretty likely. And in fact, you'd be right. The probability of S is going to turn out to be 1. We'll see that later on. See that in the next lesson. Another remark is that if A is an event, then its complement is also an event, the opposite event. Here's an example. Let's toss 2 coins, and let's suppose A is the event that I see heads, heads sequentially. So the opposite event is simply that I see anything but heads, heads. So for instance, I could see heads, tails, tails, heads, tails, tails. A bar, that's an event. A further remark is that if A and B are events in the sample space, then A union B and A intersect B are events. For example, let's toss 3 coins. Let's let the event A be that I observe exactly 1 tail. So you could list those out. Heads, heads, tails, heads, tails, heads, tails, heads, heads. Those are the 3 possible outcomes from your experiment corresponding to the event A. The event B I'll define as no tails are observed, and that clearly is heads, heads, heads. That's the only set of elements where I have no tails. Finally, the event C is that the first coin in my sequential outcomes turns out to be heads. And you can see that I have heads, 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 tails, heads, tails, heads, heads, tails, tails. And like I said, in each case, in each element, in each outcome, the first coin is always turning up as heads. So let's look at the union and the intersection of a couple of these guys. A union B in plain English is at most 1 tail is observed. That just means 0 or 1 tail, and that's A union B, and I take the union of those 2 sets. So I get heads, heads, tails, heads, tails, heads, tails, heads, heads, that corresponds to A, and I add on to that, no tails were observed, heads, heads, heads. You can see how easy that is. On the other hand, if I'm interested in the event A intersects C, so that means that I'm intersecting exactly 1 tail was observed with the first coin must be heads. And so I take the intersection of those 2 sets and I get heads, heads, tails, heads, tails, heads. Great. So this ends lesson 1. We'll go to lesson 2 in a second, in which we learn about the definition of probability.